let's get started then. So I'm Brian. I'm a professor of chemistry at Brigham Young University. I've been here for 22 years, and so I helped. So I kind of developed the labs with lots of help from a lot of people, and um, and so the original idea came as a grad student when I was at Berkeley. And the whole idea was I saw students as a TA just cookbooking and not learning anything as they went through lab. Um, and I grew up, my father was actually the chief software engineer for Apollo. And my dinner table conversation was how to write code. And, uh, and so and so I kind of combined a lot of ideas that that what we teach in a real lab is vital, but we also are missing the ability to teach students how to think, how to make mistakes, how to design experiments, and how to deduce what to do when things don't work out right. And so the whole idea of developing these labs was to create an environment where students can make mistakes and we don't have to tell them what to do all the time. And so given the current situation, these are, I think, an acceptable replacement for real labs. But when we get back to some kind of normal, I hope that these labs get used as a augmentation, as something to help students so they understand what they're doing in the labs. So with that, what I'm going to do is kind of divide this. So I'll divide this into three chunks. Um, First thing I'll do is I'm going to talk about the client and how it works a little bit and what you find there. And then I'm going to go start with organic chemistry and then end with general chemistry and kind of show how they work. They all kind of work the same way, but they all have their own little personalities because the subject is different. So I'm going to share my screen here and minimize this, and I'm going to launch the client. So what a student would do is a student would download this client from our website, or you can copy the links and put it into your course materials. Doesn't really matter. We can give you those links, and they download this and install it on their Mac or Windows. And then once they get it installed, this is what they'll see. And they'll see tabs for the labs, worksheets, license, and settings. Everyone here is higher ed, so they wouldn't have to touch settings at all. Settings just changes the level of the worksheets that are included. So what a student would do is they either purchase their own codes for $25 and insert that code, submit it, and activates their product for a year, or we sell you a code and it has X number of uses on it, and then the students can reuse that same code, and we just track how many times the code gets used. If you really are interested, we can integrate that code distribution into an LTI for your LMS, but usually that's something we do for like really big applications. So the labs are really designed to be open-ended. They're like, the metaphor I like to use is, imagine you're in a real lab, you open the door, you go in, and it can do anything. And that's the idea behind our labs, is they're just virtual doors. You go in, you have a lab bench, and you can do whatever you want. The problem is, how do you use those labs to teach with? And so we provide a preset set of lab activities we call worksheets. Sometimes worksheets has a bad connotation, but these are lab activities. And the lab activities are designed to be drop-in, where you say, hey, student, here's your lab activity, go do it. And they pretty much do this in a self-contained environment, and then your job is to tie it into what you're doing. But you don't have to use our lab activities. You can develop your own, you can modify ours. So don't think that this is everything the lab will do. It is only a small fraction. So for example, if we were in chemistry, we have a higher ed set, and then they're divided into different categories, and say, hey, what if I'm teaching thermodynamics and I want to teach about heat of combustion, or I want to talk about specific heat, or I want to talk about enthalpy and entropy or Hess's law, each one of these worksheets would have a background, and then it would have a set of instructions, and then they collect their data. We help them through their calculations, and then we discuss what that data means in terms of these questions and assessments that we ask them. So it's a drop-in solution. But it's certainly by any means the only way that you can do them. So each of these worksheets are correlated with the labs, and so that's how they kind of work. I can come back to them a little bit, and how you do it. You can download these PDFs. You can distribute them from your own LMS system if you want, or just tell them to go grab them from our client. And you can convert them into whatever form you want. It doesn't matter to us. So that's kind of how it works. Here's the labs. They would click it would say download. They click download. They install each of the products they're going to use. And here's the worksheets. And you can assign these worksheets, and they go together. So let's say I told you I'd start with organic. So with organic chemistry, we have 2 lab benches. So each of the products have these lab benches, and each of the lab benches is kind of like a self-contained, open-ended place to go do a set of experiments. So this is our landing page. Here's where you can get help. We have very detailed help on each of the different lab benches. What assumptions we make, what limitations that are there, getting started, overview. Most people don't use it, but it's there nevertheless. And over here, we have these same list of worksheet titles that we had in the client. So what happens is that you pick one of these worksheets, and then you would come down here, and the student would find, the assignment that you did, and you would click on this, and it would take them to the lab and set it up so that they could start their experiment. So has a little summary of what the goal is for each one of these. For organic, I always recommend you start with this one because it's the most step-by-step detailed one that teaches how to use all of the different elements inside of the lab. So it's a very good intro one. And then you start down to some of these. So you don't have to use those. You can just click on one of these icons. So I'm going to start with synthesis. So I'm going to give you a warning here in that I may be a chemist, but I'm not an organic chemist. And I'm a materials chemist and do solid state physics. So I know a few examples, but if you have organic chemistry questions, email me and I will pass those along to my colleague, Merritt Andrus, who helped me develop this lab so many years ago. So all of the labs are the same in that they all have stock rooms, they all have these lab benches, equipment. They're all different because you do different experiments. So in this lab, we kind of have where the reaction happens. We have the setup in the stock room, and then we have all of our analytical equipment over here to analyze products. And so each one of these named reactions creates a set of starting materials, all right? So you can pick any of the starting materials you want, regardless if it's Diels-Alder or an aldol or whatever it may be. You can pick the one that you want to define the starting materials you want. So once you define your starting materials, there's nothing constraining you to say, hey, I have to do an esterification reaction, okay? It will do any reaction that the reagents and setup will allow you to do. So it's open-ended in that way. So once I've defined my starting materials, I then now have to say, okay, which ones do I want to make a certain product? So if my target was some type of ester, then I have to go through here and say, okay, which starting materials do I need to get to that product? So I'm going to pick this acid. So I click it and I add it to my round bottom flask. You can see that there's a solid. These are liquid bottles. So, if I picked just another acid and I did some reaction, then that's what you would see the reaction happen for 2 different acids. So you are allowed to have 0, 1, or 2 of these reagents. So if I pick this alcohol and then I add it, then I'm going to see my mixture. Now I can add, but although I don't have to add it in this order, it can be any order that you do it, but I can add my solvent or not add a solvent. So I don't need a solvent for this. So I'm going to drag my round bottom. So once I do that, my stockroom is closed, which means I can't add something else now that I'm out here. And so here's my starting materials. Now I have to decide, okay, what's my reaction conditions? Am I going to use a condenser? Am I going to use ice? So here's some ice that I could add. Maybe I decide I don't want the ice, so I'm going to, I should be able to get this ice and get rid of it and put it back again. And so I can do any combination of ice or heat or nothing. I can add a condenser to it. So I'm going to go add my condenser. I'm going to go add my heat, but sometimes they're going to make mistakes, right? So like, what if they forget to add their nitrogen? So it's a sealed system. And what happens if they decide to start this reaction and then, they start advancing their time, and then it's going to blow up and show them a consequence of what happens that, hey, I forgot to add my nitrogen. So I'm going to clean up, add my starting materials again, and come back there. So now I'm going to do it for real. So now I have these 14 reagents that I can add. I can add any one of these to the reaction mixture. Okay, so they have to know which is the right one, or maybe they don't have to add anything. And so we have an outcome for whatever reagent they may use. So I added my nitrogen, my sulfuric acid. Here's my condenser. Here's my nitrogen. I'm going to add my heat. And now I'm ready to go. Now, I didn't have to do any of those. Any order was fine. It would have been okay. So now we're ready to go. I'm going to click my kind of start button so the reaction starts. So now the idea is, how do I know what's happening? Well, obviously, we decided to put what's going on in the flask on the chalkboard so they can learn what's happening. But you would do a TLC. So here's a TLC. So here's our starting material lane. Here is our product lane. And so you see, we are already starting to see some product. So I can save that to my lab book. So here's the lab book right here where those TLCs get saved, and you can open them up, see what they saved there. So now we can say, hey, I'm going to go advance myself 10 minutes and go do another TLC. Did I finish yet? How fast is it going? It looks like it's going pretty fast. My spots are getting smaller. But we use real kinetics here, at least what's published in the literature. So it's first order, almost always second order kinetics that we use, and with the appropriate rate constants. And so we can save this to the lab book, close that, and advance our time a little bit more. Notice that if you do a TLC, it advances the clock as well because it takes time to run a TLC. So now I know that I'm done, obviously over there. But the idea isn't for them to be in the dark so much as it is to learn what's going on and prove their steps by collecting the right data, by saying, okay, here's my TLC, and I can open my lab book and say, yeah, I did this at, 5 minutes, and this one was at down here at 25 minutes, and so on, so that they kind of know how long the reaction happens. So now I know my reaction's done. I need to work it up. So I'm going to drag my SEP funnel, put it on there. So now I have my product mixture at the bottom. Now I get to choose which is the right aqueous reagent to use. So sometimes you're going to want to rinse with an acid or base or just water, and we allow any of those outcomes. You can do counter current extractions. So you can drop something into the aqueous layer if you want to separate it. Up to you, and this one isn't the case here. So I'm going to go add my water. Now I have my aqueous layer, which has nothing, and I have my organic layer up here. And I'm going to go drag my organic layer. And by doing that, we go through a rotovap step to get rid of any of the light volatiles. So now I'm left with my product, and you can say, well, that wasn't very hard, but the whole idea isn't to give them step-by-step instructions as much as it is to say, hey, you want to make 3-methyl-butyl phenylacetate, you know, how would you do it? What are the right conditions? Not just to have them make it, but do it under the right conditions and understand the kinetics associated with it. So now you have to say, okay, now how do you prove you made it? So now we have these different analytical tools. You can still do a TLC and say, hey, this is, you know, pretty nonpolar, and let's go do an NMR. So you click on the NMR and drag your NMR tube and plop it on top, and now you get the NMR spectra. You can zoom in, okay? We have the peaks labeled, and we have these integrated these areas under each of the peaks that they can use. And I can save this to my lab book. And so now Brian, I can do carbon-13.
So Brian, that was, I guess, going to be my question. So those numbers are area under the peak?
Yeah, so what we did, was we labeled these peaks, and then we knew the areas, because all of these NMRs come from Sigma, so they're actual real ones. And we took the actual areas under the peak, and what we did is we created a random number and then made all of these areas relative to some random number. So you take the smallest area, like the 79.507, and divide it by through, and that would tell you the relative number of protons for each one.
Okay. And I guess while I'm on the line, do you have the actual steps, like for example, for the worksheets, if you pick a worksheet and not just, you know, make something, do you have the actual procedure that should be used recorded?
That's on the worksheet, right? So we're trying to provide a level of structure difference. So sometimes the worksheets tell you how to produce things, and sometimes you want to give students something where they actually have to figure out the process.
Right.
So
there's a whole range of levels of instruction.
But for us, is there, so we don't have to run through and see if their procedure would work or not. Do you have the actual procedures like in a single document?
I would have to contact my colleague Merritt Andrus to see if he still has all of that stuff when we developed it, because we had to do all that because we had to go through and account for all the different permutations and outcomes. And so
and you did a great job of that, because I went through and I did a lot of those.
Yeah. So we have answers to all of those worksheets, but I don't know that we actually have, we have answers to the worksheets that we can provide you. Okay. But I don't know how much detail that we have in those worksheets that tell you the quote ideal route to get to the product.
Right. I just don't want to have to go through all the experiments and figure out the time, you know, and all
Understandably,
that.
Yeah.
Those should be in the worksheets, I think.
I'm going to pull them up and check them right now, and I will confirm.
It asks the question, like, how long does it take to finish the reaction? But there's no way of knowing that from the worksheet. And then while I'm at it, the only other thing.
We provide how long it is, because the answers, so that you don't have to do it. You can just look at the worksheet and know what it is.
Exactly. So if I had the answers, that would make it a lot.
Yeah, no, we have answers for all of those worksheets.
Oh, okay.
Then, yeah, so if you just email us, we are happy to, we just don't want to post them online so that students can't get them.
Do that, no. And the same for the unknown numbers for qualitative organic chemistry. Is there a list of those that you provide? Okay.
Those are all in that answer sheet. So you just email us and we'll be glad to pass the answers, the instructor manuals with all the answers and unknowns out to you guys.
Okay, thank you.
All right. All right, any other questions? These are good questions. All right, so I just kind of want to show you all of the different analytical stuff that we have. So we have FTIR. Again, these are real spectra. Here's mass spec. Mass spec was calculated based on fragmentation patterns and stuff like that, but it's based on real data. And so, you know, obviously some schools, some classes, you're not going to use the mass spec. That's okay. You know, sometimes you're not going to use carbon-13, but, you know, for modern, you know, when we first wrote this, so we developed this back in like 2002, I think. You know, carbon-13 wasn't even taught in class, but now carbon-13 is pretty regular. And so we've included carbon-13 in mass spec and how to do it. So some things I'm not going to show right here, but, you know, if you had a mixture, all right. So let's get rid of this guy.
I'm going to interrupt for just a second while you're prepping there. The answer key for the instructors does tell how long each experiment takes and the ideal starting materials, and it gives a lot of detail. I just checked for you.
Okay, great. Thank you.
So let's say that you had a reaction mixture, you could do a distillation. So you can drag that, add the nitrogen. If you don't add the nitrogen, you get the thermometer pops off. And so you can come over here and actually distill this. So you had a mixture, it will distill over into your collection flask. And so I collected, it's empty, so there's nothing in it. So anyway, so you can distill and separate. We do have recrystallization. It's not very complicated. It's really a matter of you know, taking light volatiles off as a way of just purifying the solid that maybe has some solvents or other in it. But it's not really it's not really meant to be a separation technique, except for the light volatiles. So that's just an example. You know, we also have a spectral library for all of these different spectra. So you can go through and, you know, see spectra and compare them. It's strange, at least for BYU, students don't really use the spectral library very much. But to me, it's like, wow, I can compare all my spectra and know the answer, but they don't use that. So anyway, this is a synthesis lab. It's really robust, because a lot of your advanced reactions, and so that's how it kind of works. So on the other bench is Qual, and the idea here in Qual is to allow give students a real chance to identify unknown compounds. So, but give them lots of data to go do it. So, so what we have here is we have different functional groups, and those structures you see are known. So those are compounds that they can play with, that they can use and know what the answer is, to test their ability to interpret the spectra and have some practice to get some confidence. And then, so for example, if I pick an aldehyde, here's these 3 different knowns that they could select and put into their flask. And here's an unknown, and it has a number. So that's what was referred to previously, was we have these unknowns, and the answers to these unknowns are given in the instructor guide. So if I add this unknown, and then I take it out to my cork ring out here in the front, I get unknown number 210. So you see it on the chalkboard, and you get the boiling point, percent carbon, percent hydrogen. And the idea here is, again, do your spectra, identify your peaks, prove it, not just say what the right answer is, but prove that you know how to get to the right answer. So we can, again, do your spectra if you want. Here's your NMR, but you can also do these wet tests. So I take an aliquot, put it up here on my stand, and I can go through and do each one of these wet tests. So here's a Jones oxidation. I take it and I add it, and we show a still picture or a video. We show a video when time is important, that shows the results of a test. And so this one's positive. And so students would go through and just go through and do all these wet tests. So a worksheet, for example. So if I brought up the client, went to the worksheets, went back to organic and came down to qualitative analysis, right? I could go to this aldehyde here worksheet, and so we would have them write. So we give them instructions, CH analysis, melting point, boiling point, the TLC we have them do, principal functional groups and line positions on the FTIR, the proton NMR, what's the functional groups, and then we have them put their own unknown number, have them write the name and write the structure. And so this would be a qualitative analysis assignment. And so that's how it works. It's really powerful for students to do a lot of practice.
So Brian, could you also show how a student could submit the same information in our lab book?
Yep. So the alternate approach to doing unknowns, besides the numbered unknowns, is to go here to random. Okay. So this practice unknown here, it's the same thing as clicking on the clipboard. So it's really not different. The random ones though, so let's say I do aldehydes, it gives me an unknown now that is not without a number. So it's in our database of about 270 so unknowns. It's in that database, but they don't know the number, so they can't share that information with people. So it's the same thing. You just go through, you don't know, you go do the test, and then when you're all done, you go to your lab book. So here's all this data that I selected before, but then you're going to see report, okay? And they click on report, and then they would write down my answer and click submit. And then we show them what the right answer is. And then what they would then do is they go to file and click save, and clicking save then would let them save this to this notebook to the desktop, and then they could take that file and upload it into a LMS or email it, and then have you or the TAs, I always have my TAs do this, download these files and look at their results and then compare how close they were, because once they submit this, they really can't cheat. And if they want to go do it all over again, it gives them a new random unknown, and there's so many of them, it's in their best interest not to cheat. So anyway.
And you can certainly have students require them to write a lot more of the notes or even answers to questions in whatever assignment you're giving them in that notebook. So you can maintain it as a lab notebook, or you can have them do it separately with whatever type of worksheet, either ours or your own, that you would do it along with it. So that lab notebook we see as a way for a student to explain their procedure, explain what they observed, and then they can submit that to you.
Brian, someone came to my door. How did you pull up that worksheet from the lab, or did you do that?
So I went to the client, and I went to, so I'll go back to the beginning, is I go back to organic chemistry, and then I went, and so they're all divided into different groups of worksheets, and then I went, so I knew that I wanted a qualitative analysis, so I went through these worksheets.
Got it. And
then we have all of these different worksheets. So we even have a general unknown that could be anything out of all of them, and it's pretty challenging actually.
Yeah, okay. Thank you.
All right, so these are just PDFs. Again, what you could do is open the ones you want and save them externally and deliver them in their LMS system, in your LMS system, or just have them grab it from the client, doesn't matter.
Or we can share the Word files with you if you want to edit and change in any way you want.
Yeah, we'd be glad to do that. All right, any questions about organic?
Yeah, I have a quick question. So when it comes to the lab book, because I saw that for the qualitative analysis, they could, download the lab book information and then submit it. Is that also possible with the other experiments, with like the general ones?
Oh yeah, you can.
So where I can get a physical copy of their, not physical, but a copy of their lab book.
Absolutely.
Yeah, so you can, I mean, you could, if they're doing general chemistry, you can have all their titration data and inorganic data and gases, it's all in one file. And so you can really see a general picture of what they've learned throughout the whole year in one file.
The lab books don't share between general chemistry and organic chemistry.
Right.
But within each product. So what they can do is they can create these different sections, for example, like, you know, experiment 1, and then you can also go here and add a new page to experiment 1, and then they just go use these arrows to navigate between their pages. And then you can also create a new section and name that. And then you can go organize, and then you use these arrows to go between sections. So it's a way for them to record what they're doing and their procedures, and for you to grade them. So it's a great way to have them share their process and their thinking.
Is there any way that you know that you can convert that type of file into a Word file or a PDF file so that they could just submit a PDF?
So the answer is yes, it is possible, but we haven't written the conversion. It's text-based XML formatted code, but we just haven't done that. Bandwidth is our limit.
Sure.
Yeah, that's always something that's been on our things to do, but we just haven't gotten to it.
Okay.
And then we as the faculty have any, anything that we need to do to manage their activities, either through Blackboard or through your software program?
No, the faculty shouldn't need to do anything to manage it.
No.
So how will they submit it to us, through Blackboard or online?
Oh, they can just, whatever your learning management system is, or they can just email. They can send you those lab book files that they generate through email or through the LMS.
So it's compatible with the Blackboard Collaborate teaching?
Yeah, so those lab book files that are generated within the program can be used, it can be opened on anybody who has the program's computer.
And if it is only the students, we don't have any involvement, how do we know they are doing it or just generating the paperwork for us?
How do you know they're generating the file themselves? Is that your question?
Yes. How what is the involvement of the professor?
So here, if I understand it correctly, so here's the general chemistry lab, all right? And in the general chemistry lab, I can give them an unknown. So I haven't shown you how this works, but let's say that I give them an unknown. And so here's my lab book, and I am a, smart student and don't need notes, right? And then they come over here and they get this unknown. So let's say that they're doing chlorides. I gave them an unknown chloride. I bring this back over here and I, go do the chemistry here. So I go add the chlorides. I centrifuge that. I need to go add heat, see if I have centrifuge that, and then I decant and see if I have lead. So I don't have lead, take off my heat. Now I'm going to go add, go to pH 7, and I'm going to go add ammonia. I don't see a mercury, and but if I go and I acidify this, I get it back, so I know I have silver. So I just did a qual scheme for lead, mercurous, and silver, right? So the student would come here, they took their notes, and then they would click report, and I'm going to put silver, and that's it. I didn't see lead, I didn't see mercurous, I hit submit, and I got them all right. So what I would do is I would come over here and click save, all right? And so students doing all of this, you don't have to do any of it. So I click save, I'm going to exit out of this, and where did it go? Didn't it save it? Oh, right?
Check your documents. It went to your documents.
Oh, did it go to documents?
Sometimes if you just open the program, it'll find it directly for you, Brian.
Yeah, I just want to see where it put it. Yep, there it goes. So let's go move it to desktop so I can do that. So here's the file, right? So here's what my class would do, right? Is I would go to my, so we use a custom learning management system for BYU. Rewrote it because we didn't want to pay Blackboard. And so this is my current class, and I'm going to go be as a student. So I'm going to go pretend I'm a student. I'm going to go to my assignments. And what we have down here is we have lab 12, lab 11, and you know, they have a little button here that says submit. And so they would go and submit this and view and submit. And so it's not letting me because I'm not really a student, but they would just grab the file and upload it. And then what I do, so I'm going to go back as an instructor. What I would do is I'd come back here to my grades. So let's be FERPA honest and don't look at my students, right? And I'd go to my lab reports. And so here's what they've done is like lab 10, they've uploaded this. And then what I would do is come over here and do a batch download. And I would download all of these files in one swoop. And here's those grades. And so I open this folder and it's got everybody's Excel spreadsheet, but this would be a lab book. And then but it appended all their names, and all I would do is then I would then go back to chemistry and have my TAs go do this. So I would start chemistry and come over here on this lab book, open it, and then I would just open the file and I would path over to wherever they're at. So I'm just going to open the one I saved. And I could go here and start, if these were lab book files, I just start opening them one at a time, look at what they did and give them a grade. So it's a manual grading, but it's really easy to get all the files and go through and do it.
And if students were sharing their files between them, you could see really easily that they were the same because each of the students' unknowns are randomly assigned differently. So nobody should have the same unknown.
Okay. So the faculty does not have to observe them doing the experiment or making up the lab report.
No.
They will just
No.
assign them the activity, and then they will submit their work.
Correct.
Yes.
Okay. Thank you.
Does that help? Did we answer?
Yes, very much.
Okay.
Thank you. And that works for chemistry, organic, as well as Gen Chem.
Yes.
And physics.
Okay, good. Thank you so much.
So, so yeah, I mean, that's the way that we kind of use it, but everyone can use it differently. We tried to make it pretty general to kind of fit, because I know I'm old enough that everyone has their own style and how they manage. And so I don't like being crowbarred into certain ways, but we do have constraints. We used to have a back-end management system to manage unknowns, but nobody ever used it and was such a pain to use that it just wasn't worth maintaining. So we tried to make it simple. And in the end, we have a couple of papers we published back in 2006 and 7, I think, that really show that it's really just doing the labs and going through and doing the assignments where the students really learn. So, all right, let's move on. So some of you wanted general chemistry, and works the same way, okay? Same thing with worksheets. We have about 80 different worksheets that cover 90% of the curriculum, and what I would call the experimental curriculum. It doesn't do bonding because bonding's a theory, but it does show, cover much of what you're going to cover in general chemistry. We really have lab benches that are really good duplicates of what you would do in a real lab. And we also have 2 labs over here, quantum and gases, that are really extensions or experiments that you would not normally have a student do. All right. So let me show you a few examples of these. These would be what we call the quantum lab. And so this is a pretty unique lab. So here's an optics table, and the idea here is, here's the stock room, but instead of having chemicals, you know, what we have here is the PChem stock room, where we have lasers and electrons and super light bulbs and spectrometers. And students can bring these out and build experiments. Now, obviously, to say, hey, go do milk and oil drop, you know, most of them aren't going to be able to figure it out just by saying that. They're going to need some guidance. So our worksheets have these kind of guidance to them. We also use presets. So here on our clipboards, we use, in these labs, we kind of have more presets for the experiment. So if I say, hey, let's go do Rutherford, you know, so what we do is we bring out alpha particles with a gold foil and a phosphor screen. And so we would then just go do this experiment. So, you know, again, you need some structure so they kind of know how to guide them to understanding Rutherford's experiment. But as a teacher, for me, you know, I read in the textbooks and they say, oh, Rutherford, in one paragraph, they'll say, Rutherford shot alpha particles at a gold foil and discovered that the atom was mostly empty space. And maybe they show a really nice picture, but the students never know how he came to that conclusion. So the idea here is to have them go do that. So, you know, for example, you could move this gold foil off and you see alpha particles coming through and you see a little spot on the phosphor screen, you know. Maybe you turn off the alpha particle, shut the shutter here and say nothing. Now open the shutter. So what does this mean? What does this big spot mean in terms of why is it there? And then we step them through the logical deductions that get us there. We have them move the phosphor screen over aside. What do you see? You still see the alpha particles being scattered at a wide angle. Now move it right here. And so you click the persist button here and you can see where they're at. And I can click save and save this experiment to my lab book. So if I open my lab book, you'll see here is that same same experiment that's being done. And so you're able to go through this and step them through what's going on in this experiment. But it's more than just doing that experiment. You can lead them through and say, well, what happens if I change my metal to gold? So I'll get rid of my gold and I'll click my box of metal foils and I'll come over here and pick magnesium and zoom back down. And then I put magnesium in there and see, I get a bigger spot, but it's not nearly as big. And notice how few I'm getting. Now we can ask them why, what's going on here? You know, why did Rutherford choose gold? You know, and what would have happened if he would have chose magnesium or something like that? And so we allow them to do all of these experiments. And so, interest of time, you know, we're hours almost up already, but I mean, you can do lots of things here. Milk and oil drop, right? I can adjust my electric field and use this to measure the charge of the electron. We have Thomson, 2-slit diffraction, so we can change the color, and we can change the slit spacing, and then you can change the intensity and talk about Heisenberg's uncertainty principle here. And so I can click persist and save where all of these photons hit and show that, you know, what the meaning of wave particle duality is in Heisenberg's uncertainty principle. So lots of PChem type things you could do. Absorption of I2, for example, you can do, zoom in on this spectra. But other simple ones that you do in general chemistry, like photoelectric effect and photo emission of hydrogen gas. So here's the visible spectrum, there's the full spectrum. and zoom in on it. So that's what the quantum lab is. I showed you really quickly the inorganic lab. The idea in the inorganic lab is, this was actually the first one we did. This is version 4 of it, and you have all of these cations that you can add, any order, any combination, and we show you a real picture of what's in it. All right, so they could see, so this is a known, they can centrifuge, they can do a flame test. So it's all designed around qualitative analysis, but the purpose of qual is to teach them the reactions of the chemistry. So you can also add these reagents. You can heat it up, smell it, you know, measure pH. And so I can go pH 10 or NaOH, or go back to pH 7, and we'll show them so this is based on all real chemistry. Like that Rutherford experiment was real chemistry. Those spectra was real data. And so this is what's behind these labs. We can give them unknowns in general chemistry. We also have calorimetry. So in the calorimetry lab, we have coffee cups, dewars, bomb calorimeter. You have metals. So here's a drawer, 4 drawers full of metals that you can measure the heat capacity on. Organics, so we have like 50 different organics that you can do combustion calorimetry on. Salts, reactions, create unknowns. And then again, we have clipboard. So what if they want to do, you can do Hess's law. What if they want to measure heat of solution? So here's sodium acetate, for example, and drag that, and we see the temperature. We see the temperature increasing over time, accelerate. So you have balances and ovens and ice beakers. So all of these different experiments they can do in calorimetry. And lastly is titrations here. So in the titration lab, drawers full of beakers, pipettes you could use. We have pH meters, conductivity meters, and different acids and bases. So students can titrate any acid with any base, or any acid with an acid, or base with the base. We have reductants and oxidants they can do titrations with. So they can pull out their different ones, and I'm just going to use a preset here. So what if they want to standardize NaOH standardization, for example? So here is a bottle of KHP. So they can zoom in, measure the mass. So here's our weigh paper. They can drag this over, put that in the beaker, and we already have some water in the beaker. So, you know, notice that we have this balance is tiered. So the water's in it, we drag it over, have the stir plate on. I've already filled up my burette, already calibrated my pH, my conductivity meter. Here's a graph. So I'm going to go drag these over. Here's my pH meter. So we're measuring the pH, measuring the conductivity. We added phenolphthalein, and I'm going to click save, save data. And I can start this titration. And as it goes, we're saving this. They can save this to their lab books as well. I'm saving data. You can slow this down to be different rates. So we'll just go fast, get this over with, so you can kind of see the endpoint. But this is a titration. So obviously this preset built everything, but you don't have to do that. Different experiments do different lab activities, preset the lab differently based on what we're trying to teach. So there's the titration, the endpoint. I can click stop, click on my lab book, and click on my, there's my plot, and oh, I got to click stop here, and then go back to the lab book. And now here's my data. So here's all that data. They can copy that data and paste it into spreadsheets to go do their analysis, or you can have them go do the analysis just by using the indicators. So just to show you how detail oriented we are, there's a barometric pressure that changes every day in the room, because when you measure a mass on this balance, it's an observed mass and not a true mass. So the students are getting a little bit of air. The glassware, like the pipettes and the burettes, have volumetric errors built into them, so they don't deliver perfectly. And there's also random errors thrown into reading the volumes and such. So that's a crash course through the general chemistry lab. They're super powerful, and lots of good learning that students get to do with them. Any questions?
I just have two comments. The first, and for feedback, that if you want to use it or not, I don't care. It's hard to find that IR worksheet because it's under alkene experiments, and it's really
what?
The alkene. I'm sorry, the IR worksheet that you recommended doing for the first experiment, which I totally agree with. It's very difficult to find because it's under alkenes, and it's really an esterification. So I had to look through all the possible worksheets to find it. So you may want to just put it under its own or under esters or something.
Good idea.
Yeah. Okay, that's a good idea. I think there was a reason why we did that. I can't remember why.
Because I was looking all over for it, and I had to go through each and every one.
Yeah, it's number one.
Yeah. The other thing, I think I mentioned this to you, Brian, the other day, but you probably have a lot on your mind. Instead of typing in the names of compounds, if you went with CAS numbers, it would not only be unambiguous, but it would teach students how to look up CAS numbers.
That's a good idea. Well, we're in the middle of, it's nothing really relevant to you now, but we're in the middle of converting all of our labs over to HTML5. So we have some prototypes. They're not done yet. They're not going to be done for a year, but here's like our titration lab. It's kind of how it works. And, it's the same algorithms underneath. And so it's going to be a good time when we reinvent these labs for HTML5 delivery that we can kind of, we'll deal with a lot of those issues.
Okay, I thought I'd throw it out there.
No, that's great.
Yeah, thank you.
Okay, well, thank you guys. It was a great demo, and I'm already working on incorporating this into my syllabus. So we'll see how it goes.
Any other questions from anybody?
All right, we good?
Yeah, thank you so much, Brian. I'm gonna use this.
All right, thank you very much.
Thank
Yeah,
you.
thank you. Thank you
All
for
right,
your time.
thanks.
Bye. Bye.
All right, to stay in touch, give us emails if you have questions.
Yeah, who should I write to about that? Anyone?
Just email info@beyondlabs and we can get them to you.
Okay, cool. Thank you.
Or you can use that contact page. It'll be the same thing.
Okay, thanks.
All right,
Bye now.
bye.